Good morning. In Taiwan, I think must be an evening in Maryland, East Coast of America. And welcome to the Mini Moon seminar, online seminar. And today's speaker is Dr. Tim Livengood. And Tim remind me that we met 30 years ago at AGU. And actually, it was the Livengood that I remember very well. I remember giving a talk and he was really bouncing. It left you a deep impression. I hope that he would do the same thing today.
I've calmed down a little.
I calmed down a little, but just a little. Tim, he was graduated from Johns Hopkins. I think in physics and astronomy. And then he's now working at Maryland, University of Maryland, Department of Astronomy, as an associate research visitor. And he has a long line of participation in missions. And interestingly, some of them have very interesting names like Dali, Picasso, Matisse. I wonder how he ended up doing that. And he's an expert, of course, on atmosphere, planetary atmosphere, on some very, very tricky measurements using infrared. And he will tell us a little bit more about today. And today's topic is on the moon. But I think that in future, he will have much more to tell us. Tim, floor is yours.
All right, thank you, Wing. So I'm Tim Livengood at University of Maryland. And I'm going to talk to you today about measuring water vapor at the moon. I want to be clear, we have not yet measured water vapor at the moon. The presence of water vapor at the moon is at this point purely theoretical. But the consequences, if we measure a significant quantity, are substantial with respect to the future of human exploration on the moon, and with respect to understanding how water comes to be at the moon, and therefore, potentially in other airless bodies in the solar system. I want to bring some attention to my my co-authors here, who are co-investigators who have been working on this project with me for some years. Carrie Anderson, Gordon Chin, and Tilak Hewagama are all on the science team. Paul Rossett is our instrument scientist for the instrument that I will be talking about at the end of this talk. Nagar Hassan is our system engineer, and Barhanu Balcha is the receiver engineer. All right, so as I mentioned, we're working towards trying to measure water vapor at the moon, with the first question being, why do we think there is any water vapor at the moon? If you had asked anyone, any lunar scientist, say in August of 2009, is there any water at the surface of the moon? They would have said that at best, there might have been some trapped in rocks. And so you could discuss a chart like this one that indicates sources and sinks of water vapor, or rather of water in lunar regolith, and transport processes, but they would have assigned very, very small values to almost everything here. The sources would have been described as very small, outgassing very small. Photolysis by solar ultraviolet would have been high enough in the most person's view to eliminate anything. And the orange arrows on the left showing horizontal transport of water, either by lunar rotation of material in the surface or horizontal transport of gas above the surface, would have all been assigned to a value of 0. And a lot of the reason why we believe that is, of course, because we went there. Now, this picture is much more recent than the Apollo missions, but it is a good example of what the moon looked like for the Apollo astronauts, as well as the Surveyor landers, the Lunokhod landers, and the Luna missions, and then, of course, the more recent missions to the surface of the moon. It is dry and dusty and no apparent signs of water. And so we had a very simple understanding. Moon dry, earth wet. That's the end of the discussion. Nothing else that we had to talk about. But then, of course, I picked August of 2009 as a very specific date because in September of 2009, there were 3 papers that came out in the same issue of Science. As it happened, they were carefully timed to coincide with the Division of Planetary Sciences meeting, which was in Puerto Rico that particular year. I was there. Came out at once, led by a paper from the Moon Mineralogy Mapper instrument on the Chandrayaan-1 mission. So India's first mission to the moon, which was intended to use infrared spectroscopy to determine the temperature of the lunar surface and to identify mineralogy in the surface. But then an unanticipated discovery was the presence of 3-micron absorption, which is shown in the upper right of this plot of different derived mapped quantities. Or zoomed in on it, this is what it looks like. So a number of gores underneath the spacecraft mapping out a 3-micron absorption feature that coincides with water of hydration in minerals that are observed on Earth. Now, the reason why it is very incomplete is that the Chandrayaan-1 mission only operated for 1 month before the spacecraft failed. Nevertheless, it was very productive. In a later paper taken from these same data and mapping it in a cylindrical coordinate system, Shuai Li and Ralph Millikan were able to demonstrate the presence of this 3-micron water absorption feature, this hydration map, all over the surface of the moon, with an increase in signal intensity as you go to high latitude. But then they can't go all the way to the pole because the measurement depends on reflected sunlight. It was looking at sunlight of course, sunlight extends to all wavelengths, but it dominates 3.5. So at 3-micron, we were seeing an absorption in reflected sunlight. Now, Shuai Li also transferred this to a map in longitude, separated just by the times of day at which there were different measurements made. Of course, this is well after those actual observations were reported. This paper is from 2017, but showing that there was a local minimum in the amount of hydration at local noon. Now, this was long after it had been persuasive evidence had been provided by other instruments measuring at the same time, because at first the M-cubed team, they're called, were unable to provide absolutely definite evidence that there was a time of day variation in signal. Now, as I mentioned, there were 3 papers that came out in Science, and part of the reason why the lunar community was ready to accept this sharp change in their understanding of water at the surface of the moon is because 3 completely separate spacecraft made the measurements at different times and showed the same thing. So another paper was actually publishing data from the Cassini flyby of the Earth in 1999. The observations were almost exactly 10 years earlier than the publication of this work, when Cassini flew by Earth and the moon, and the visual and infrared mapping spectrometer observed the spectroscopy of the moon, and then nothing was done with that work for a decade, until there was an opportunity to compare it with the M-cube data, whereupon they discovered that Cassini VIMS also mapped a 3-micron absorption feature, which is shown on the right. Well, the spectra are shown on the left as measured intensity divided by the anticipated flux at the moon. And then on the right, we have dividing that out in order to show the magnitude of the reflectance and the magnitude of that absorption feature. And you can see that from 2.8 micron to about 3.2 micron, there is this substantial feature, which changes shape depending on where exactly you're looking on the moon, but was in many locations. The third paper that came out was from a mission that I happened to be involved with at the time, although for a variety of issues related to how the team was constituted, I was not involved with the paper. But I was involved with making the measurement that will be on the next slide. But this was reusing the Deep Impact spacecraft after the Deep Impact mission, which delivered an impactor to Comet 9P Tempel 1. There was a perfectly functional spacecraft left in operation. And so NASA entertained proposals for what to do with it. And we combined two proposals, one from Goddard for extrasolar planet observation and characterization, which included an element of observing the Earth as a model exoplanet, with the Deep Impact Extended Investigation, which observed, well, other comets as a further investigation of cometary comae and the composition of the coma. So I used data from one of the observations of the Earth where the Earth happened to have been occulted briefly by the moon, or actually transited by the moon. So the image in the lower left there is an actual image from the Deep Impact mission, or from the epoxy mission, from the observations I was making, where we had the moon just about to transit the daylight portion of the Earth. So we actually started when the moon was well over to the left of this, and we ended with the moon well over to the right. And we were able, in addition to getting the visual light or visible light imaging that you see here, we were also able to do near-infrared spectroscopy. So on the left side, we have the near-infrared spectrum of the moon divided by a very simple model that combines a reflectance component and a thermal emission component in order to remove the solar features and to correct for the fact that there are orders of magnitude differences in the intensity of the emission in each of these features. On the right side is an image from Jessica Sunshine's 2009 paper showing that they had looked at a similar hydration feature. Mine averages over the whole surface of the moon. Jessica used observations from 2009, June of 2009, that were much closer to the Earth, where they were able, or actually much closer to the moon, where she was able to map the depth of that hydration feature as a function of position on the moon. And so this is from Jessica Sunshine's 2009 paper in Science, showing albedo on the left side, and then on the right side in the infrared, it shows the thermal emission from the moon in the panels C and G, and it shows the depth of that hydration feature in panels D and H from two separate observations, each in June of 2009, showing that the hydration feature is least strong at the subsolar point and increases approaching the terminator. And in fact, I want to point out, if my cursor shows, yes, there, the North Pole was approximately where my cursor is pointing on the screen. So parallel, roughly speaking, to the 12% absorption depth feature that's shown right here. So there was a very strong feature. It was easy to see. Now, during the same time period as these observations were being reported, another mission went to the moon. The Lunar Reconnaissance Orbiter, or LRO, launched on June 18 of 2009, cruised to the moon over 4.5 days, and then underwent 3 months of instrument checkout. Now, that's an important time difference, because that 3 months means that at the end of that, it was right during the same time period that those 3 papers were released. Now, LRO did not go to the moon alone. It also brought 2 sister spacecraft, the L-Cross mission and the Centaur upper stage from the launch vehicle, for this purpose could be treated as a spacecraft on its own. So LRO got to the moon in June of 2009. It carries a large number of instruments. I'm going to go very quickly through them just to mention their existence. It includes, of course, a visible camera called LROC to observe the surface of the moon. It includes an instrument I work with, the Lunar Exploration Neutron Detector, and I will explain more about that later on. And it contains a number of other instruments that I'm skipping over. So the purpose of the L-Cross mission was to send the Centaur upper stage to crash into the surface of the moon with the L-Cross satellite following it in order to observe the plume of material raised by the impact. And then the L-Cross spacecraft hit the surface of the moon at about the same place about a minute and a half later. So it was a very short mission. And the impact location on the moon was chosen on the basis of early L-Cross data, or sorry, early LRO data. Now, in particular, because we were all in one place at the DPS meeting in Puerto Rico, they arranged for the impact to happen during the week we were there. So we had both the release of those papers about water on the moon, and we had this impact measurement whose purpose was to measure how much water is in what are called PSRs, permanently shadowed regions at the moon's poles. LRO was able to observe the impact and see the flash of light. So that very blurry small image in the lower left and then zoomed in the lower right is the visible light flash from the Centaur upper stage hitting the surface of the moon. It was also observed with a mid-infrared instrument on board LRO, which swept across this region and observed the hot material being ejected. So LRO was a very successful mission. It measured exactly what they were anticipating, but got much more of it than they anticipated. So they measured water, but contrary to the measurements from LRO, which anticipated about 1 or 2% by weight water in the regolith, they measured about 5%. We do not yet understand the discrepancy between those measurements, but they also measured a number of other volatile species in the surface of the moon that had not been anticipated to be released by the impact. In particular, molecular hydrogen is very hard to understand how that could be in the surface of the moon unless something like galactic cosmic rays are breaking up water ice in the surface, which then traps the H2 below the ice. But also they measured CO and then a number of geologically volatile materials, calcium, mercury, and magnesium were released by the impact as atomic or ionic species, which was unanticipated. Now, I mentioned that I also am working with an instrument on LRO. I am working with the Lunar Exploration Neutron Detector. This is a map of the moon in neutron emission that is overlain on a topographic map of the moon in order to associate the neutron emissions with the physical sites that we're familiar with on the moon. So everything that has detail in this picture comes from visible light mapping. Neutron mapping has extremely low spatial resolution. Where you see blue in this map, there is an overabundance of relatively high energy neutrons with an energy on the order of 100 keV and greater. Where you see red is a suppression of both the high energy neutrons and what are called epithermal neutrons, neutrons with an energy of about 1 eV up to about 100 keV. So that is in the green channel. You can see, of course, there is very little green in this because at mid latitudes, the neutrons are roughly evenly mixed in the way I've distributed the color stretch here. So we have a suppression of the epithermal and the high energy epithermal neutrons in the polar regions, as expected from the original expectation that there would be some water trapped in the polar regions of the moon. And that suppresses the energetic neutrons and converts them to low energy thermal neutrons, which is the red channel in this map we're seeing. So everywhere that you see it going towards the red it means that there is more water in the lunar surface. So there is clearly an enhancement in water in the surface in the polar regions. Actually, I will take a moment to be specific. There is an enhancement in hydrogen in the surface. The neutron flux responds to the abundance of hydrogen in the surface, but the only reason until L-cross that we thought there would be hydrogen trapped was because of being in water. Now that we have the L-cross mission showing that there is water and molecular hydrogen in the polar regions, we just don't understand that. Now, LRO has some other instruments, including a UV spectrometer. And after the measurements by Deep Impact and M Cubed and Cassini-Vims, a member of the UV instrument team, Amanda Hendricks, evaluated the signature of water in the spectroscopy in the UV. So on the left is the raw measurements of the amount of water that they estimated, and on the right is an average. This is measurements near the equator, measuring with respect to time of day on the lunar surface. And you can see that she has a suppression in, or a reduction in the amount of water very close to noon and slightly asymmetric, although it's not clear how strong the data are for representing that asymmetry. So that seems to indicate a greater amount of water in the morning, then a decrease at noon, but then a recovery in the afternoon. So that's interesting. To that extent, it supports what was seen with the near infrared spectroscopy from Deep Impact and M Cubed, but the spatial distribution is much narrower here. The suppression in the ultraviolet signature is concentrated very close to noon, whereas with the infrared measurements, the largest amount of water is very far out at the terminator and then decreases continuously up until noon, or at least it appears to. So there is a discrepancy there that is presumably related to the skin depth that is probed by the wavelength of light. These measurements are at about 200 nanometers, whereas the other measurements are at 2.8 micron, or about 2,800 nanometers. And so much longer wavelength, and so able to penetrate more deeply into the surface. So the ultraviolet is only seeing whatever is on the actual skin of the surface, whereas the infrared sees at least a somewhat deeper skin. But if you want a deeper skin than that, you need to go to the neutron measurements. The neutrons probe about a meter deep into the surface, so several orders of magnitude more deeply than what is seen by either of the optical spectroscopy methods. Oh, sorry about that. My dogs just got very excited here. Let me encourage them to leave the room. Nope, just the one dog wants to leave the room. There we go. Sorry about that. So as it happens, we have two neutron instruments that are relevant, or two detectors on LEND that are relevant to the water that we're trying to understand. I don't need to go into the details, but this is related to that map of the different neutron energies. So the map on the left is the higher energy neutrons. The map on the right is the lower energy epithermal neutrons. In both cases, what you see here is a suppression near the dawn terminator in the flux, certainty in the measurements. So high time resolution sacking of the measured neutron flux. So you can see it's quite noisy. And in each case, I have averaged it over the breadth of that interval in local solar time and determined the uncertainty from that measurement in order to show how it varies with the time of day on the moon. Now, unlike the measurements in the ultraviolet and the near infrared, the neutron flux does not care about solar illumination. In fact, it is based on the galactic cosmic ray illumination of the lunar surface. So we can see all times of day. We can also see the polar regions and see into permanently shadowed regions in the poles where the other optical techniques cannot probe. But I'm not going to be speaking about that today. I'm going to be speaking almost exclusively about the low latitude measurements because that is the part I've worked on, but to me is also the most surprising. The other part is confirming things and that we knew and getting a better measurement of something that we were confident would be there. This is still measuring something very new. Now, a difference in these two energy ranges that you see here is the high energy neutrons probe only about 25 centimeters into the surface, whereas the map on the right, sorry, the trace on the right is the epithermal neutrons, and that probes about a meter deep into the surface. That may surprise you at first because you would think that the high energy neutrons would be able to penetrate more deeply. The reason it's different is that we are looking at what we call the leakage flux of neutrons. So the neutrons are created in the lunar surface by galactic cosmic ray impacts on lunar regolith material. Their energy is distributed over a power law by numerous collisions with the materials in the surface. The more deeply the neutron is produced, the more its energy is reduced before it emerges from the surface. So the reason the high energy neutrons probe at a shallow depth is because they do not undergo enough collisions to reduce their energy. Whereas the neutrons that probe more deeply, by the time they escape from the surface of the moon, their energy has been reduced. And so that's why the low energy neutrons represent ones that source at a greater depth and measure the hydrogen content at a greater depth. As you can see, they both see a reduction in flux at the dawn terminator at the same location, actually just barely on the day side of the dawn terminator. They see a peak in emission in the mid-afternoon, and then they begin to decline again. Now, this is somewhat confusing because wherever you see a reduction in flux means there is more hydrogen. So I have helpfully turned the same plots upside down. So now they are proportional to the amount of water. Another aspect you see here is that the high energy neutrons seem to have a greater contrast in the absorption at dawn compared to the afternoon. We have interpreted that to mean that the water is concentrated in the upper 25 centimeters of the regolith, which is consistent with the fact that the near infrared measurements see it, and is also consistent with the ability to have a diurnal variation. Because the neutrons probe so deeply, there is no way for us to simply stop seeing the existence of hydrogen. It can be in a water molecule or not in a water molecule. It would look exactly the same to us. Now I've taken these maps and or these traces, and I have transformed them into a clock dial to give you an impression of what it would look like if you could see the abundance of water looking down from the North Pole. And in both cases, with both of these, that was supposed to be green in that one on the right, something changed. But in both cases, you can see that the maximum is in this post-dawn period, then decreasing until we get to the afternoon, where we have the driest period. I should be clear, that doesn't mean there is no water. It means that it is as dry as it gets, because that is our reference measurement. And then it increases continuously through the lunar night until we get back to dawn. We do not understand that. At lunar nighttime temperatures, there should be no mobility of water molecules. The surface is about 80 to 100 Kelvin. Any water molecules that are on the lunar night side should be frozen to the surface. So the fact that it appears to be continuously arriving at the surface, we do not understand. But it is what we observe. Now we can take all of these things and try to make an estimate of what we think is going on the lunar surface. As I was just mentioning, the the challenge we face with the neutron measurements in particular, well, there have been proposals for ways to make the spectroscopy measurements appear to have a diurnal variation without actually having horizontal transport of water. For instance, if the water migrates more deeply into the surface, then visible light, near infrared, ultraviolet light could not detect it, but neutrons still would. So there is no way that a migration of water deeper into the surface could hide it from the neutron measurement. Another argument has been that perhaps the water moves horizontally by centimeters in order to stay within the shadow of rocks, because that would locally be colder than everywhere else on the lunar surface that gets illuminated. Again, that would hide it from spectroscopy, but it would not hide the water from neutrons. The neutrons have to actually move across the surface and move from one place to another in order to deplete one region and increase the amount of hydrogen and the amount of water that we see in another region. And we can estimate what fraction of the water has to be moving. All we need to do is suggest a velocity at which it could be migrating towards the dawn terminator, and then across the dawn terminator into the vacuum of the night side, where the temperature is so low that it cryopumps all of the volatiles onto the lunar surface. Well, there's a variety of possible values you could assume, but the most reasonable one would be the speed of sound. If you open a vacuum system, you'll hear a bang as air molecules hit the interior of your vacuum system. And the reason is that the molecules are actually transiting that interior volume at the speed of sound until they hit the opposite wall of a vacuum vessel. The same thing can happen on the moon, which means that the gas would be moving about 1 kilometer per second, roughly speaking. This does not need to be a very precise measurement. And from that estimate, you can then estimate, well, we know that the water is moving with the lunar surface into daylight as the moon rotates. That is at 4.3 meters per second at the equator. In order to have momentum balance, so that water can be traveling back towards the night side at the same speed as, or at the same momentum as it is traveling towards the day side, then the fractional abundance of water molecules is the ratio of the velocities. And so we can find from that that a less than 1% of the water that we measure by neutrons is above the surface. Nevertheless, that is a large amount of water molecules by the normal standards of the moon. We can apply the same kind of measurement to the spectroscopy measurement, or rather the same kind of estimation method to the spectroscopy measurements. And the reason why we make this is if the molecules move towards the night side faster than the rotation of the moon carries it to the day side, then the water would simply stop suddenly because it would all be depleted. So at this terminator, the fact that it does not stop suddenly means that we can use this momentum balance. If it were traveling more slowly than the estimate, then we would never have a minimum point. It would just have an average at all regions. So we have to have this balance. So we can use this to get an estimate of how much vapor there is above the surface. In fact, we can construct a table comparing all the reasonable estimates from various possible sources from that chart I showed on the very first slide. And we have a standard of comparison that matters too. In the first line of this chart, you can make an estimate for what is the total column abundance of molecules above the surface that is consistent with our expectation of a surface-bounded exosphere. And that is about 3 times 10 to the 14 molecules per square centimeter. Well, we can go down to the bottom of the table where we estimate the abundance from the neutron flux and discover that it is about 3.5 orders of magnitude greater than the surface-bounded exosphere. If we estimate it based on the variation of the near-infrared spectroscopy, now a problem is we don't know how deep in the surface it measures, but we can make an estimate for the minimum depth in the surface, which would be about a micron into the surface to account for the wavelength of light that measures it. And that is still a couple orders of magnitude greater than the abundance for a surface-bounded exosphere. Now, other arguments have been made for what could make water at the surface of the moon, including solar wind impact on the surface and micrometeoroid impact on the surface. Those would both exist in competition between delivery and removal by solar ultraviolet. And so you can estimate what abundance of vapor would be consistent with that delivery and removal process. And those are both well below a surface-bounded exosphere abundance. But then finally, the biggest argument against the possibility that there is a surface-bounded exosphere is an actual measurement by the LADEE spacecraft. LADEE flew a highly elliptical orbit over the moon with its lowest point at the Dawn terminator and observed using a mass spectrometer an extremely low quantity of water, many orders of magnitude less than the requirement for a surface-bounded exosphere. And so one of the biggest challenges that we face in any measurement we make is that the LADEE mission sets a very, very low upper limit. The question then is, how can we live in a universe in which the LADEE measurement was made and the other measurements also are made? One possibility is that the processes at the surface of the moon prevent the LADEE measurements from observing the water vapor atmosphere that is consistent with the direct spectroscopy measurements of the surface and their diurnal variation. Another possibility is that the LADEE measurement is accurate and has been accurately interpreted. And so the phenomena that cause us to see a diurnal variation in spectroscopy and in neutron flux must be an unanticipated novel phenomenon. And in fact, it needs to be two different novel phenomena, because as I already mentioned, there are ways to hide water molecules from reflected sunlight, but there is no way to hide it from the neutron flux. And so if there is a variation in neutron flux at the surface of the moon at the equator that is not measuring a diurnal variation in water, then it means there is a novel phenomenon we do not understand that varies that measurement, and a different novel phenomenon that controls the spectroscopy. And so we have built an instrument with the intention of testing all of these propositions. And that instrument is called SSOLVE, the Sub-Millimeter Solar Observation Lunar Volatiles Experiment. SSOLVE is built, and I will show you pictures in a moment, but it has not been flown to the moon yet. We are proposing to go on a future NASA mission, but we have not been selected yet. So the goal with SSOLVE is to land anywhere on the surface of the moon that we can see the sun, and then stare at the sun. Sorry, I'll move my cursor off. We will stare at the sun and be able to measure the water vapor in absorption against the sunlight above us. The way we intend to do that is with the instrument using a heliostat to track the sun. And then we have two receivers, one of which measures an actually it measures two OH transitions of hydroxyl that may be released above the surface or result of sunlight being broken down by solar ultraviolet at 2.5 terahertz. And then at 557 gigahertz, there is a water transition. And at 509 gigahertz, there is an HDO transition. And so we placed a local oscillator directly between those two, well, almost directly between, so that the HDO and H2O transitions will map into the same spectral range in difference frequency. And so we can see the absorption of both. Now, the chances of measuring HDO are very small. It is a much weaker transition than the H2O. The only possible way that we will see HDO is if we have the very large quantities of water that are consistent with the spectroscopy or the remote sensing measurements. But if we see that, we will really want to know where that water comes from, and the deuterium to hydrogen ratio will be one of the clues that we would want to look for to understand that. Just to give you a block diagram of the interior structure of the instrument, we will have an elevation mirror to help track the sun, but it can also be reversed to measure an internal hot load. And this is important. One of the problems with the LADI measurement using a mass spectrometer is that it is very difficult to eliminate contamination from local measurements. So far, there has only been one mass spectrometer deployed on the surface of the moon by Apollo 17, and ultimately the measurements from that instrument have all been discounted on the assumption that it was contaminated by anthropogenic sources, both from the lunar excursion module releasing gases and from just the distribution of water vapor and other gases released by the astronauts while they were operating at the surface. And then finally, the instruments themselves still outgassing. Now, I'm not sure I believe that because they were still measuring water vapor 10 months after they landed. I would have thought that would all be gone. Nevertheless, it is hard to be sure with the with the LACE measurement from Apollo 17. And with LADI, again, there are ongoing problems. So our plan with SSolve has always been to have a very strong calibration plan. And so we can turn our instrument to measure our internal path and determine whether we are seeing any water absorption inside the instrument itself in the path between our mirror or our entrance aperture and the receivers. And we can also turn the elevation mirror to look at the ground nearby, which will thermally emit radiation and enable us to measure any water vapor between us and the nearby surface of the ground. And between those two measurements, when we compare to the strength of any water absorption feature we see looking at the sun, we should be able to determine whether we are looking at an intrinsic lunar atmosphere or looking at an atmosphere that is sticking to the lander itself. And so the plan would be that we would land near dawn, look through the water vapor atmosphere at the surface of the moon, which is estimated here, at the sun, and then make our measurement of the total water vapor column. And you can see also I've illustrated that the LADI mission swooped down over the Dawn terminator, reaching a minimum altitude of about 4 kilometers. So either the water vapor that appears to come from the materials at the surface of the moon does not get as high as 4 kilometers, or it does get that high, but the LADI mission was unable to measure it. One possibility being that the transport velocity across the surface, in order to account for the diurnal variation, is very similar to the orbital velocity of the spacecraft. And so it may be that it was simply immersed in water and was unable to make any difference regardless of the orientation of the spacecraft. An idea of the absorption feature that we anticipate, this is an estimated measurement. The uncertainty in the left corner there is a 3 sigma uncertainty in a 1/2 second measurement compared to the absorption at various concentrations that we have anticipated. So you can see that in our first half second of measurements on the surface of the moon, we will immediately establish whether the moon has a surface boundary exosphere or not. And of course, the expectation is that it is a surface bounded exosphere. If so, that means that I need to reinterpret my measurements from LEND. If I have to prove that I am wrong, I would rather that I am the person who makes the measurement to prove it. SSolve will enable me to do that. If the abundance of water vapor at the moon is less than the surface boundary exosphere, our first 10 minutes of observation will enable us to probe the other elements of that table that I showed you in order to get down to an extremely small concentration. And if it turns out to be that small, we can continue making measurements over the course of a couple of weeks at the surface of the moon. But at that point, we would be working to prove that the LADEE mission made its measurement correctly. And we don't know right now what the result will be. This is just an estimate of what the OH transition would look like. The OH really cannot exist in a collisional atmosphere. If it did exist in a collisional atmosphere, there would be interactions that would turn it back to H2O and free oxygen, or actually, yes, free oxygen. So this is the same table again, but I would like to show you some measurement, or rather some pictures of the SSolve instrument. This is SSolve in our laboratory at Goddard, waiting for its thermal vacuum testing. Actually, at the time of this picture, it is a hollow box because the receivers were not yet installed. This is what was inside it. It shows some of the sub-millimeter optics, but most of the electronics were not inside. These cables that you see are purely for testing purposes on the motors, the mechanisms that enable it to turn to track the sun. This is thermal testing of the instrument with some of the electronics installed to make sure everything would survive. And just to give you an idea of the size of the instrument, this is SSolve, the heliostat in the laboratory with, on the right-hand side are the members of the mechanical engineering team that actually built the heliostat. On the left-hand side, the tall fellow is our instrument scientist, Paul Rossett, and I am about the same height. And next to him is Nagar Ehsan, our system engineer. And that is the end. I'm just leaving on a pretty picture of the moon. And so if you have any questions, I am ready to take them.
Yeah, thank you, Tim, for a very, very comprehensive talk about what you have been doing. So there's still a number of questions that would be people might like to ask. Let me ask the people. You have questions. You could raise your hand or write it on the chat box. Do I see anyone raise hands? Or you could just turn on your mic and ask. So Lin Chi-Hong, you said you have questions?
Yeah, okay. So thanks for your great talk, Professor. So I have two questions is because you mentioned that we can use this near infrared light and also the neutron flux. So we can roughly to locate the water ice in the moon. But my question is because indeed the moon is the natural satellite of the Earth. And Earth have the human made a lot of infrared light from the cities, from the their country. So my question is, will in this kind of near infrared light source from the Earth to cause interference of this observer? So this is the first question.
So the near infrared light from the Earth is not a significant contributor to the surface of the moon. While you can certainly see the Earth, it is several orders of magnitude weaker because it is reflecting sunlight. So the direct sunlight that reaches to the moon is much greater than the sunlight that reflects from the Earth and reaches the moon. But also, I have actually tested this proposition because we do have extensive measurements of the Earth itself as part of our effort to measure the Earth as an analog for an exoplanet. And I have verified that you cannot see any of the city lights that occur on the surface of the Earth in our images. Now, our images have very poor spatial resolution. A discovery shortly after the launch of the spacecraft was that the camera was out of focus. And the people at Ball Aerospace who built the camera said that they have learned their lesson and they will never again fly a camera that does not have a focus mechanism. It was supposed to be built perfectly focused. The reason for no mechanism was because the original mission to observe an impact on a comet expected that everything important would happen over such a short time scale that if there were a mechanical problem on the spacecraft, there would be no opportunity to fix it. So they tried to minimize the number of mechanisms, but it did have a consequence. For our purposes, we wanted to ignore spatial resolution and just make our measurements of the whole disk of the object because we wanted it as an analog to an exoplanet. For that purpose, a blurry camera was perfect. Nevertheless, I did try stacking up the data from the Earth just to see if I could see the city lights, following a suggestion from Kelly Beatty at Sky and Telescope. I could not see a thing. And there have been other studies too. So the Earth is not contributing to that portion. There is still the possibility that scattered light in the instrument could contribute. And while I tested that, or rather I made measurements to, the way that I processed the data did the best I could to eliminate that effect in my measurements. I need to revisit before I publish some other work to make sure I do it right. The work that Jessica Sunshine published was looking with the Earth behind the spacecraft, looking directly at the moon. So there was no opportunity for scattered light from the Earth to appear in the spectrometer, except for the light that was actually reflected from the moon. And that's a very small component. Sorry, you had another question.
Yeah, so my second question is because, as you mentioned, so there's a water signal peak. It's appear on the morning of the Earth, of the moon, and finally they will be getting weaker in the afternoon of the moon. But in the next day of the moon, this peak will still appear again. So my question is, it sounds like very unreasonable because if these water signals are getting weaker, they only have one reason, which is the water is disappear from the moon surface. So under such a high temperature of the moon, I think the most reasonable explain is the water molecule emission from the moon because moon gravity is very weak. But that also means the moon will lose water. Why that water people come back again? Because that means the water is a moving under the moon ground. So I don't see the rock or the other substance under the moon is movable because this is too strange.
So we have looked at the possibility that water is delivered and removed from the surface of the moon every lunar day. There has certainly been a long-standing expectation that solar wind, by delivering hydrogen atoms to the surface, well, actually protons to the surface, along with free electrons, could result in water at the surface of the moon from interactions with the lunar regolith minerals. The problem is that the number of water molecules created is about 10 to the 8th molecules per square centimeter per second if you assume that every single proton in the solar wind becomes part of a water molecule. Whereas the actual number required to account for the neutron measurement is 10 to the 20 water molecules per square centimeter. There are not enough seconds in the day to account for getting that many new water molecules at the surface of the moon every lunar day. And so they cannot simply arrive and then leave the moon. Now, it's possible that something like that affects the spectroscopy, Even so, they need to have about 10 to the 16, they need a total of 10 to the 16 to 10 to the 18 water molecules per square centimeter. So again, they are many orders of magnitude greater than the possible abundance of water molecules that could form in the surface of the moon from solar wind. So there has to be another phenomenon taking place. Now, a possibility, as I said, is there could be several phenomena taking place. It could be that there are several novel things, or novel in the sense that we did not previously consider them. And so that could be accounting for separately each of the different processes that we see with a diurnal variation at the moon. Right now, we don't have the evidence to prove that that is wrong. And that is what SSOLVE would do. We can land SSOLVE if we measure a water vapor atmosphere at the moon, then that will immediately provide a way to interpret which one of those processes makes sense. If it is a very small quantity, then it means that we cannot be seeing horizontal transport of water molecules over the surface. If it is a larger quantity, however, then it means that we need to consider new phenomena, because as you say, it is reasonable to expect that the water molecules simply leave, consistent with a surface boundary exosphere. The problem is that it involves a huge amount of water. And so that part is unreasonable. So we have no completely reasonable argument for what is going on. For the large quantities, the unreasonable part is that the water molecule lifetime should not be long enough for those molecules to persist at the surface of the moon. And yet, we see them.
Okay, Chiong, you have to solve the problem also, right? Now I have a second question from Wendy Zhang. Wendy, can you ask the question yourself? I mean, the team could also see from the chat box, but I think you could ask that question yourself too.
Yes. Thank you for the comprehensive talk. So I'm just curious, how would you avoid the sunlight influence on the sub-millimeter observation of water? Particularly, you would observe the water in the daylight?
Oh, we will observe the sun directly. So the idea is that the surface of the sun, of course, is 5,800 Kelvin. Our beam is bigger than the sun because we wanted to keep our aperture very small. So the aperture is only about 4 centimeters across. And that means that the beam is about 3 times the size of, or 2.5 times the size of the sun. And so we have profoundly diluted the signal from the sun. On the good part of what's good about that is it means that we do not need to point extremely accurately. As long as the sun is in the field of view, we will see the sun. And so we see the sun as approximately 1,000 Kelvin black body. And so the absorption of water in the ground state against the sunlight is how we make this measurement. And so the water line will be extremely strong. If we get the very high quantity of water, the one that goes with the neutron measurements, we will actually see the water absorption line will saturate completely and even become a self-emission in the center of the line. If we see that, I will be extremely excited. But I am trying to make myself believe that I will not see that. But if I see it, I will be extremely excited.
Oh, thank you. So is that possible? We can use like the ALMA to test your theory?
Unfortunately, no. Even over the Atacama Desert, the amount of water is so much greater than what we are looking for at the moon that local water will absorb it. And there's no Doppler shift between ALMA and the moon. Or no significant Doppler shift. So there's no way to separate the transitions. Mm-hmm. We are considering the possibility of a test flight on a balloon platform that would take the instrument to let's see, how high does it, well, at least to several tens of kilometers, well into the stratosphere. At that point, there should be extremely little water in the Earth's atmosphere. And so then we could observe the moon directly and see thermal emission of the moon's surface with water vapor between us and the surface of the moon, if there is any. The problem, of course, is that in that case, we have no source that we can look at by looking away from our target in order to say, is that water vapor local? Is that Earth water vapor? Because we will have many kilometers of Earth atmosphere between us and the moon. Still, it would be at least a proof of concept. I will say, I cannot give you more details, but it is possible that there will be an important proof of concept measurement in the next week. And if that happens, either I will be very sad or I will be extremely happy.
Yes, and please let us know next week.
Well, it will take longer than that because it will be embargoed until we can get a publication out.
Oh, I see. Okay.
Now, Tim, so the instrument will be put on the lander. Is that true?
Yes.
And what will be the time, the mission time? Several days, or because you don't want to go to the lunar night?
So we are proposing for what is called PRISM, is a NASA program, Payload and Research Investigations on the Surface of the Moon. And PRISM, in turn, goes to a contractor to provide the lander. And so it is a Commercial Lunar Payload Services, or CLPS, lander. When you work at NASA, everything is an acronym. And so there are a number of challenges this way. The biggest challenge being none of these people has any experience landing anything anywhere. I am fervent about this because the first landing from a CLPS provider is supposed to happen in a couple of months. And I am very concerned that it will just crash on the surface of the moon. It might not, but it probably will. But by the time we get to fly, I hope that they will have proven their technology a little better. We still have a number of challenges because we cannot design our accommodation to be perfect for us. They have a spacecraft and they say, can you use it? And it is not clear because they don't want us to sit on top of their spacecraft, for example. They have a place on the side of the spacecraft where they want to put the instrument. Well, our instrument consumes about 45 watts.
Wow.
And it has to radiate that heat someplace.
Yeah.
And the body of the spacecraft would be directly behind us so that we would not be able to radiate efficiently. Now, we planned for this by anticipating that we would only operate on a 1 out of 6 duty cycle, so 10 minutes out of each hour. Nevertheless, we have some concern that we may not be able to cool our instrument well enough. If we had just a different design, because they provide enough power, but we need to be in a different place. We need to be on top of the spacecraft so that there is nothing but empty sky behind our instrument. Then we can radiate all our energy away, maintain a healthy temperature, look over the side of the spacecraft to look at the surface of the moon. It would be wonderful.
So it sounds more like a kamikaze mission.
Well, I mean, they all are because they're one-way trips. And so when you get there, the nature of the mission is that you get 1 day. Then you get lunar night. We are looking at the possibility of how to make the instrument survive the night. But then we have new problems because with a radiator big enough to radiate 45 watts, we need to have a way for it to have thermal louvers that close down and make it less efficient at night, or rather less efficient as a radiator. but the louvers have mass. And so that creates a mass problem for fitting on the accommodations. And we still need too much energy at night to keep the electronics at a functional temperature, well, at a safe temperature. So right now we are not yet there. We can do all the science we want to do during the day. The problem is that they would land maybe a local solar hour after dawn. What I would really like would be to turn on a lander that is in the nighttime about a human hour before the sun comes up, so that we can stare at the horizon. So when the sun comes up, it will come into our field of view and immediately give us a grazing incidence measurement of the lunar atmosphere, looking at the sun across the surface, so that we can track it from the moment it rises as it goes through the sky overhead and then sets on the other side. That would be the perfect measurement.
Mm-hmm. But that would be too big for orbiter too, right? Your instrument.
Actually, I think we are in a good position for an orbiter. This particular instrument would not be a good choice. Because, well, the first thing is it has a very heavy component for the azimuth tracker to do this, to follow the sun. Well, we can take that off, which will immediately reduce the mass of the instrument by about 10 kilograms. Mm. So that brings us down to, I think, about 15 kilograms total. The 4-centimeter aperture would give us a beam on the surface of the moon that is about 1 kilometer across, or let me check my memory, about 1.5 kilometers across, which is a factor of 2 better than the diviner instrument, but really not as good as what we ultimately want. We don't care for spectroscopy of the water vapor. That would be fine. But in order for our instrument to be useful to the lunar exploration community, we also want to be able to measure the temperature of the surface from its self-emission. And for that, we want to be able to measure it at a scale that is relevant to astronaut transport, which means we need pixels about 100 meters across. And so we need an aperture about 30 centimeters. So we would need to redesign it. The thing is, we know we can do all of that. And so we decided not to propose for an instrument development program this particular round of NASA work, because we know we can build it. What we need is an opportunity that says, propose an instrument for an orbiter. Then we can do it. Mm-hmm. For an orbiter, we can look at the surface, the daylight part. I mean, even at 100 Kelvin, our sensitivity is so good that in principle, we could measure the water vapor over the surface, except there won't be any. So we can measure the surface nighttime temperature. We can measure the temperature in the permanently shadowed regions, where the temperature gets down to about 25 Kelvin. And we could still measure it with small pixels with high quality measurements, plus or minus 1 Kelvin. But on the day side, where we would have water as a vapor, we would be able to measure it above the surface at all daytime temperatures, which are between about 150 Kelvin and 400 Kelvin. And so map out the distribution of water vapor as a function of time of day and as a function of latitude. It would be wonderful.
And the instrument is no good for lunar gateway.
Sorry, for what?
You don't want to put it on the lunar space station.
The gateway would not be good.
Because
it is too far away.
Too far away and too dirty to fill with the envelope in the water vapor.
Right.
Yeah. Okay, Tim. You spill all the beams now. We're waiting for your great discovery or great success in a week time, and I thank you. We want to thank you very much for the very enlightening talk, and I must say that you're still the same 30 years afterward.
Well, thank you very much, Wing. Okay,
Okay.
thank you, everyone.
Thank you.
Have a
Thank
good
you.
day.